Okay, so for our first one up here, we add those two numbers, we end up with 37.23 centimeters. When we add or subtract, what are we looking at for determining our rounding? We're looking at precision, right? Place value. This one is precise to the nearest hundredth. This one's precise to the nearest tenth. So the least precise one is the tenth. So that's where we have to round. So here's the tens place. That 3 is saying it's going to stay 37.2 centimeters. This one here, we multiply that out. We get 1469.7. That'll be inches squared, square inches. When we multiply or divide, we go off of accuracy, which is the number of significant digits. So when I'm looking at this one, how many significant digits does it have? 3. That one's easy. They're all, none of them are zeros, so we just count the digits. This one here, do we count the 0? No, that is a 0 we don't count. When there's no decimals, zeros at the end of the number don't count unless they have that little bar to indicate them. So this is 2. So we're going to have to round this off to 2 digits. 1, 2 right there. That 6 says we round it up to 15. Like that. 2 digits. Now, kind of a weird little example we can run into might look like this. See what you get there. So, what do we get when we add? We get 1703.74 inches. Where do we have to round to, though? This one's precise to the hundredth. This one's precise to the 100. So I have to round to the hundreds digit. I added 3.74 and it didn't change the number. The reason being is the error in this number right here is plus or minus 50 inches. So the error in that measurement is bigger than what it is we're trying to add or subtract to it. So it doesn't make sense to add or subtract it. The only reason I'm showing you this example is because it wouldn't make sense to even try to combine those two numbers. Because of the drastic difference in their degree of precision, they're meaningless to each other. Let's look at another one that's kind of weird. 32.65 inches times 36.753 inches. See if you can get that one rounded off to the right number of decimal places. So here, when you multiply those, what do you get? So 1199.98545 inches squared. But let's look at our significant digits here. Are we rounding to a place value, or what do we have to round to when we multiply? Multiply its accuracy, or a number of significant digits. How many significant digits here? 4. Here? 5. So we're going to round to 4 significant digits. So we start at the beginning of the number count. 1, 2, 3, 4 digits. We're going to round after that. But what's that tell us we have to do? Round up. Well, we round up. That's a 9. There's going to be a 0, carry the 1. That's going to make that a 10. So a 0, carry the 1. We get 1200. I can't write it like that, though. Why can't I write it like I just did? That's only 2 significant digits. We calculated to 4. Got to put a line above or below that 0 to show that that is a significant 0. That is now indicating that this does have 4 significant digits. Well, there's a reason I showed you that example up front instead of just throwing you a quiz and saying, here's this example, see if you can figure it out. For those of you following along at home, that might be an indication that there is a quiz coming up. Any other questions on this stuff? Now, as I said, I am going to give you a quiz, but I do realize that this is stuff that's beyond what you guys need. I mean, this would be if you were in the engineering or design side of things, you would need to then it would be very important to continue your significant digits through calculations. You can't calculate, like I did up here. You can't take a number here that's only measured to the nearest 100 inches and work with it with other numbers that are more precise, because it doesn't make any sense to have a plus or minus 50-inch error. Because everything you work with is going to have a plus or minus 50-inch error or greater after that. So you gotta work with numbers when you add or subtract. You got to work with numbers that are close to the same degree of precision at least. Okay, well, I'm going to pause this and hand out the quiz. Okay, there are a few of you still working on the quiz, and as always, feel free to take as much time as you need to finish up. For right now, we're going to take a look at just a little bit of our new material. Actually, just kind of a review of where we ended off last class and finished it off just a little bit. So we talked last class, we're talking about tolerances, where if we had something like this, that created a range. What was the possible range of values there? Well, 1.2 inches minus 2 thousandths, which would be 1.198 inches, to 1.2 inches plus 2 thousandths, which is 1.202 inches. Correct? Look familiar? And we talked about unilateral tolerances, where we have something like this. Of course, that means, yeah, we can't be any smaller, but it can be larger. Where we really prefer it to be exactly 3/4 of an inch, but if we got to be off a little bit larger. And remember, we did talk about the difference between why we would do this over just creating the equivalent bilateral tolerance. The fact that this is telling us that we really do want it closest to this. We don't want it right in the middle of the range. We really want it closer to the bottom end if we can. So anyway, what I want to look at next, just briefly, is what happens if two parts fit together. For example, on a lot of your heavy equipment, you have what's called locator pins. You go to install a piece to it that has to bolt on. There's actually a little pin that sticks out, so that when you put that large piece on, that you slide that pin into a hole, and it kind of holds it in place while you get bolts started on it. Well, those locator pins need to be able to slide in and out relatively freely. That's what we call clearance. They don't have to fit tight because they're not really holding anything in place once it's there. It's just needs to slide on really quickly and loosely. Give it a rough location while we're waiting. So let's say that this is a 1/4 inch locating pin. And since it's not a vital piece, we're going to give it a relatively rough tolerance of 5 thousandths. So then over here we have the hole that it's supposed to be fitting into. And again, since it's not like going to be an acting connection, a fairly rough tolerance. So these tolerances, of course, give us a maximum and a minimum size for everything we're dealing with. For our pin, what is the minimum size, the smallest that pin could be? 245. Good. What's the largest it could be? 255. For the hole, what is the smallest it can be? 260. And the largest? 270. Now, they're fitting together. So we're looking at something called a clearance. Now, depending on where each of these is at within their range, we have either a minimum clearance or a maximum clearance. The minimum clearance comes when the pin is its largest and the hole is its biggest. What's the difference between them there? 5/1000 of an inch. 5/1000 of an inch should still be adequate for them to slide in and out freely. Get some crud on it, it might be able to fill up 5/1000 of an inch, but that should be okay. The maximum clearance is when the pin is at its smallest and the hole is at its largest. What's the difference there? 25 thousandths. That's quite a bit, but in this case, since it's not a working connection really, it's not a huge deal. It's not going to vibrate back and forth and wear out or anything. But if it were a working connection, that would be a huge deal. Does anybody know what the standard clearance is for threads on a bolt? 1/64. Yeah. It's usually about 0.02, 2/200ths of an inch, a 50th of an inch. But that's between a 64th and a 32nd. So that is basically your thread clearance. That 25 thousandths is pretty close. By the way, if you ever worked with a bolt that's a 32nd of an inch clearance, they won't stay tight with a crap. What's that? Well, it happens every now and then, even with pretty good quality. You can see here, just a 5/1000ths tolerance, or 5/1000ths allowance, I should say, gives you a range of 20 thousandths difference. So if you have a bolt where the bolt is at its minimum dimension and the nut is at its maximum dimension, yeah, you can have a pretty good tolerance between them, a pretty good gap between them, a clearance. And the more clearance there is, the more likely that nut is to come loose on the bolt and vibration. That's why when you look at military grade, by the way, you hear all the time, oh, the military spent like $800 on a bolt. And that's just it. The clearance, you could not hand tighten a nut on one of those bolts, period. You couldn't even hardly start a nut by hand on one of those bolts. The clearance between a nut and a bolt for most military grade stuff is less than 10 thousandths. Way less than 10 thousandths. It's very, very tight. But it's made that way so that they don't vibrate loose. I mean, you don't even need a lock nut on them. They will not vibrate loose because they're that tight. There is no room for vibration. Unfortunately, the process for producing that is not easy. Generally, what they do, they don't have a special process for producing military grade bolts and nuts. They'll just produce maybe 10,000 bolts and nuts, and they'll test them. They will test them. They'll take them out and they'll test them to see which ones have the clearance, and they'll send that pair out. A lot of the stuff that you get for military grade is actually paired up. And out of that 10,000, yeah, they may get 40 or 50 that meet that tolerance, but the military is paying for the run of the whole 10,000. In fact, what's that?
That's why I say $100.
Exactly. And to be honest, most of the time, those companies that supply military parts, because I did do some engineering work for one for a while, most of those companies that supply military parts are taking a loss on what they sell to the military. That $800 that they charge for those bolts, let's say they get 30 good ones out of here. So they're only getting, what, like $24,000? That's not paying for those bolts. Not paying for the cost of them. Where they make their money is they take that surplus that isn't good enough for the military and they turn around and sell it to other vendors. It's still good enough for everybody else. That's where they get their profit. So the military contracts generally don't completely cover their expense, but it's called the residuals. They sell off the stuff that's not high enough quality for the military. Most of your military surplus stores are not military grade equipment. That's the stuff that was produced for the military and didn't make tolerance. Some of them are actually are cast and then machined down, run through. It's actually run through a die. Both those, well, actually, I shouldn't say they're not cast. They used to be. Now they're actually done through a stamping process, kind of a forging process. It's just a rod that comes out. It is cut off. Then the head of it, once it's cut into a blank like that, the head of it is actually pounded with a set of dies. They'll actually turn it into a round head. Then it's just snipped in a die. It actually runs through, and it kind of like a mill, just a multi-head mill that mills them off. And then it's actually, it goes into a clamp that clamps onto it and actually turns it into a die now. So that is clearance. The other side of it would be something called interference. If you're looking at a car motor, you have like the frost plug. The frost plugs in the block of a car, they're not threaded in or anything. The only thing that holds them in is that plug is actually slightly larger than the hole it goes into. So this might be your frost plug. And it's being pressed into a hole in the block. And what's holding it in is that interference, the fact that the plug is larger. So this plug might be 0.75 inches plus or minus 0.005 inches. The hole is right. 0.74 inches plus or minus 0.005 inches. So now as we look at this, both the plug and the hole have minimum and maximum dimensions again. What is the minimum dimension on the plug? What's the smallest it can be? 745. Maximum? 755. The hole minimum dimension? 735. Maximum? 745. So now if we're looking at our interference, our minimum interference comes when the plug is small and the hole is large. What's that difference there? 0 inches. Does that mean the plug won't stay in? Chances are it will. There's usually a speck of dirt or dust or something on it that'll hold it in place. But it's not going to take much to pop her back out. It's not going to take frost to push it out. Just a hot engine will probably push it out. Then, of course, our maximum interference comes when the plug is large and the hole is small. It's 20 thousandths. 20 thousandths might actually be a little bit difficult to press in. This is one of the reasons why aftermarket parts are a problem. You ever been told about the process of aftermarket parts? Why they're called aftermarket? What's that? Well, what they do for an aftermarket part, that's kind of it. What they do for an aftermarket part, you have the part that is produced by the company. You have the company that makes the car, they actually have the blueprints and the plans for each part. And they make parts. And they may sell those blueprints to another vendor to make parts for it. So they're approved, there may not be actually Ford or GM parts, but they're an approved vendor that makes those parts. Aftermarket parts wait for either the automaker or one of their approved vendors to make the parts, put them out on the market. They go out and they buy the part, and they go home and they reverse engineer it. They measure up all the pieces and they come up with their own plan based off of that part. Now, the part that they bought has tolerances in it. So when they make that part, and when they measure that part, they might be taking a part that's at the very small end of the dimension or the very large end of the dimension. And so that their design might be off by a few thousandths to begin with. But then they have to guess what the tolerances are on those dimensions when they're making their own plan as well. And generally, in order to keep prices down, the bigger tolerances you have, the less scrap you have, the less rejected parts you have. So if you can guess those tolerances bigger, you're going to have fewer of your parts that you're going to test and throw away when they come off the line. So they get out there, they're going to have larger tolerances and likely to be more further off. I mean, I've actually seen people buy an aftermarket frost plug and it slides right into the block. They don't have to press it in. Because they may have bought a part, and when they reverse engineered, the part they bought was actually on the small end of the tolerance anyway. So they're producing stuff that's at the small end. Now, they don't just go out and buy one part. They usually go out and buy, 10, 20, however many, and they measure them up and take an average. I mean, they're not totally stupid, but there is a chance that they could buy 10 parts and all of them are on the small end or all of them are on the large end of that range, or at least the average is on. Oh, yeah?
Yeah. They go to the OEM.
Okay.
Get the parts. They have a deal with them where we actually make their parts for them. Sometimes if they're behind.
Oh, sure. Oh, cool. So you're not just stealing their parts.
They're going to try to sue us if our parts too similar.
Really?
We change in our blueprints by like fractions of a degree.
Yeah. Sure. Yeah, I know the whole copyright and patent laws are it's really weird at what.
Well, we had a Rockwell mark in one of the parts,
Mm-hmm.
and it was actually 10,000 off in position, what it was positioned in
Their part.
So they thought we were copying everything, like things in the wrap. And then
Sure.
we took our company to court and we were just like,
Yeah.
really? Almost sued.
That whole intellectual property thing is really, really strange. It's nuts. So in your book, page 228 to 229, that's exercise 7-10. And page 231 through 236, exercise 7-11. That'll wrap up our first hour class. It is time to take our break, so if you want to take your break, let's go ahead. We'll come back at 8:30 here. I'll give you a little bit of time to start on this, and then we'll start our second lecture.